The periodic table, developed by Mendeleev, was intended to illustrate the arrangement of elements using atomic weight as the basis of classification. However, this arrangement showed some anomalies, like elements with higher atomic weights were placed before elements with lower atomic weights. For example, the atomic weight of cobalt is 58.94 and that of nickel is 58.68. However, the Mendeleev's periodic table places cobalt before nickel. Such anomalies were resolved when the modern periodic law designated atomic number as the criterion for classification. In this lesson, you will learn in detail about the modern periodic law and the modern periodic table. At the end of this lesson, you will be able to explain how the modern periodic table is arranged, explain the reasons for classifying elements on the basis of atomic number, describe the features of the modern periodic table, and identify the trends observed in the modern periodic table. The modern periodic law was developed by Moseley, an English physicist. This law states that the atomic number is a better basis for classification of elements than atomic weight. This law formed the basis for the modern periodic table. Atomic number is the number of protons in an atom. It is also equal to the number of electrons in the atom, since an atom is electrically neutral. For example, the sodium atom contains 11 protons and 11 electrons. Therefore, the atomic number of sodium is 11. Similarly, the atomic number of magnesium is 12. Since the atomic number of magnesium is higher than that of sodium, magnesium is placed after sodium in the modern periodic table. Electronic configuration of an atom is the arrangement of electrons around its nucleus, which affects the properties of the atom. Bohr, a Danish physicist, tried to explain the behavior of atoms through his atomic structure theory. According to his theory, electrons are not located randomly around an atom's nucleus, but occur in definite electron shells. Electrons in the outermost shell of an atom are the ones involved in chemical reactions. These electrons are called valence electrons. The shells in an atom can be named alphabetically as shell K, L, M, N, and so on. Each shell in an atom has a limited capacity for electrons. The K shell can accommodate 2 electrons. The L shell can accommodate 8 electrons. The M shell can accommodate 18 electrons. The N shell can accommodate 32 electrons. As the lower shells are filled up, the additional electrons are placed in more distant shells. Normally, elements show the following properties based on their electronic configuration. An element with 8 electrons in the outer shell is stable and does not normally enter into chemical reactions. For example, argon is an inert gas and does not react with other elements. However, if the outer shell has less than 4 electrons, the elements are reactive and give up electrons in chemical reactions. For example, sodium has 1 electron in the valence shell. It gives 1 electron to chlorine to form sodium chloride. If the outer shell has more than 4 electrons, The elements normally accept electrons in chemical reactions. For example, chlorine has 7 valence electrons. It accepts 1 electron from sodium to form sodium chloride or common salt. Let's examine the features of the table. Elements are arranged in the increasing order of atomic numbers. Horizontal rows in the periodic table are called periods, and vertical columns in the table are called groups. Elements in the modern periodic table are arranged in 7 periods and 18 groups. You can locate an element in the periodic table by referring to the relevant period and group. For example, sodium belongs to the first group and the third period. You can observe trends in the properties of elements as you analyze them across periods and down groups. Let's look at the basic trends in belief. The properties of elements change gradually from left to right in a period. As an electron is added to the outermost shell. For example, sodium is highly reactive and magnesium is less reactive as compared to sodium. There is a drastic shift in properties between the last element of a period and the first element in the next period. For example, neon is inert, whereas sodium is highly reactive. Elements in a group display similar properties because they have the same number of electrons in the outer shell. For example, sodium in period 3 and potassium in period 4 belong to group 1. Both these elements are highly reactive and metallic in nature. Elements are placed in periods based on the number of shells in their atoms. That is, the number of shells in the atoms of all elements in a period is the same. While moving from left to right in a period, the atomic number increases by 1 unit at each step. This means that a valence shell electron is added to the atom. Consider the example of the elements in period 3, which have 3 shells, K, L, and M. The third shell starts getting filled as we move from left to right in the period. Thus, the first element in this period, sodium, has 1 electron in its valence shell, while the last element, argon, has 8 electrons in its valence shell. Let's take a look at the basic characteristics of each period in the table. The first period is the shortest period and contains only 2 elements, hydrogen and helium. The second period contains 8 elements, from lithium to neon. The third period also contains 8 elements, from sodium to argon. The fourth period is a long period and contains 18 elements, ranging from potassium to krypton. The fifth period contains 18 elements, starting from rubidium and ending at xenon. The sixth period contains 32 elements, from cesium to radon, which also includes 14 lanthanides, from cerium to lutetium. The seventh period is incomplete at present and can accommodate 32 elements, which includes 14 actinides from thorium to lawrencium. It will be filled up as new elements get discovered, as is expected. In addition to the 7 periods across, the periodic table is classified into 18 groups vertically. The classification in groups is based on the number of valence electrons in an atom. The number of valence electrons of elements down a group is the same. Therefore, the elements in a group show similar physical and chemical properties. Let's take a quick look at the properties of the elements in each group to examine their similarities. If you begin with group 1, this group has 7 elements: hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Elements in this group contain one valence electron. That is, their general outer electronic configuration is ns1. Because of their configuration, they enter into chemical reactions easily. That is, they are highly reactive. All these elements form basic oxides that react with water to form alkalis. So the elements of group 1 are also known as alkali metals. For example, sodium reacts with oxygen to form sodium oxide, which then dissolves in water to form sodium hydroxide. Let's now look at the elements in group 2. The elements of the second group are beryllium, magnesium, calcium, strontium, barium, and radium. These contain 2 electrons in the valence shell. That is, their general outer electronic configuration is ns2. These elements are also known as alkaline earth metals, since they hydrolyze easily to form alkaline solutions. For example, magnesium oxidizes to form magnesium oxide. This compound can be dissolved in water to form magnesium hydroxide. The next group is group 3. The elements in this group are boron, aluminium, gallium, indium, and thallium. Group 3 elements have 3 valence electrons. Hence, their general outer electronic configuration of atoms here is ns2np1. These elements form covalent compounds that are formed by mutual sharing of electrons. For example, boron trichloride is formed by the sharing of 3 electrons between boron and chlorine. Let's move to group 4. The elements in this group are carbon, silicon, germanium, tin, and lead. These elements contain 4 valence electrons, and their general outer electronic configuration is ns2np2. The elements in this group combine with halogens to form the respective halides. For example, carbon combines with chlorine to form carbon tetrachloride. In the same way, silicon combines with chlorine to form silicon tetrachloride. Next is group 5. The elements in group 5 of the periodic table are nitrogen, phosphorus, arsenic, antimony, and bismuth. These elements contain 5 valence electrons, and hence their general outer electronic configuration is ns2np3. These elements react with hydrogen to form hydrides. For example, nitrogen combines with hydrogen to form ammonia gas. Similarly, arsenic combines with hydrogen to form arsine. Let's now consider group 6. The elements of group 6 are oxygen, sulfur, selenium, tellurium, and polonium. These elements contain 6 valence electrons, and hence their general outer electronic configuration is ns2np4. These elements react with hydrogen to form hydrides. For example, water and hydrogen sulfide. Group 7, the group of halogens, is next. The elements of group 7 are fluorine, chlorine, bromine, iodine, and astatine. They contain 7 valence electrons, and hence their general atom electronic configuration is Ns2np5. The elements in this group are also known as halogens because they have originated from the sea. These elements have the tendency to gain electrons and become stable. This property helps in the formation of compounds with alkali metals. For example, chlorine accepts 1 electron from sodium to form sodium chloride. The last group is group 8, or the zero group. The elements in this group are helium, neon, argon, krypton, xenon, and radon. All these gases, except helium, have highly stable Ns2np6 electronic configuration in their outer shell. Helium has 1s2 configuration. They are also known as inert gases because they don't react with other elements